All right, chapter 13, examples. We are going to start with number 3 from your textbook in chapter 13. It says, show that a commutative ring with the cancellation property under multiplication has no zero divisors. So remember, a zero divisor is if you have an a that's not equal to 0 and a b that's not equal to 0 and ab equals 0, then a is a zero divisor. So let's start this by saying let AB be equal to 0 and A is not equal to 0. Now, we know 0 times anything is 0, correct? So 0 is the same thing as saying A times 0. Well, we could use left cancellation here. So left cancellation of A, and we get B equals 0. Well, what this tells us is that we do not have a zero divisor because B had to end up being 0 then. So we've showed there's no zero divisors because we have this cancellation property. So first one done. Next one, number 5. Show that every non-zero element of Zn is a unit or a zero divisor. So real quick, let's remind ourselves, what's a unit? A unit is a non-zero element that has a multiplicative inverse. So units have inverses under multiplication. Zero divisor, that's A such that AB equals 0 for some non-zero B. So A and B were both not 0. So in order to prove this, let's let K be an element of Zn. Now, if the greatest common divisor of K and N equals 1, K is a unit. And this is something that we should know from chapter 12 when we were going through our notes. Our set of units is going to be UN. So anything where your greatest common divisor between N and that number is 1. So basically things that are relatively prime. So this is something that we should know. So we're not going to have to do a lot of talking and discussing as to why that's true. So we have our case when K is going to be a unit. Now let's see our case when we get K to be a zero divisor. So either our greatest common divisor is 1 or it's not 1. And it would have to be greater than 1. So our second case is if the greatest common divisor of K and N is equal to D, which is greater than 1. If that's the case, then we could say that K is equal to SD. Something times D is K. And then we would have from there that K times N over D is equal to SD times N over D, which is equal to Sn. Which is equal to 0. Now how do I know that Sn is equal to 0? Well, because I'm mod n and I'm taking something times n. So it has to be equal to 0. I had to get away from having fractions before I got there, though. So we found our case for where it's a unit, and now we're seeing that as long as they're not relatively prime, then K is a zero divisor. All right, number 15. Let A belong to a ring R with unity, and suppose that A to the n equals 0 for some positive integer n. Such an element will be called nilpotent. We want to prove that 1 minus A has a multiplicative inverse in R. And it gives us a hint. Consider 1 minus A times 1 plus A squared plus all the way up to plus A to the n minus 1. So for this, we need to let A be an element of R, which is a ring with unity. And we're going to have A to the n equals 0. Let's consider what they said to look at. 1 minus A times 1 plus A squared plus all the way up to A to the n minus 1. Well, as we're considering that, why don't we just go ahead and multiply? So if we were to multiply, we would have 1 plus A squared plus all the way up to A n minus 1. That's taking 1 times everything in our second. And then taking negative A times everything in the second, we'd have minus A squared minus A cubed minus A to the n. And then we would see that a lot of canceling can happen, right? We have a positive A, cancel with the negative A. Positive A squared, negative A squared. And we can do a whole bunch of canceling. We're going to see everything cancels except for 1 and minus A to the n. Now, we know that A to the n equals 0. So this is equal to 1 minus 0, which is really just 1. Now we started with 1 minus A times 1 plus A squared plus all the way up to A n minus 1, and it now equals 1. Therefore, 1 minus A has a multiplicative inverse. And its multiplicative inverse is, so we'd say that 1 minus A inverse is equal to 1 plus A squared plus A to the n minus 1. All right, that wasn't too bad. And now we know something new. We know what an element being called nilpotent means. It means A to the n is 0 for some positive integer n. In number 18, we learn what it means to be idempotent. So a ring element A is called idempotent if A squared equals A. Prove that the only idempotents in an integral domain are 1 and 0. Okay, what's an integral domain again? An integral domain is a ring with unity that has no 0 divisors. 0 divisors again is when we have an A that's not equal to 0 and a B that's not equal to 0, but AB does equal 0. So let's kind of look at this and let's see here. Let's consider A an element of R, where R is an integral domain. And A squared equals A. Now, A squared equals A implies that a squared minus a equals 0. Now this implies that a times a minus 1 equals 0. Since we're in an integral domain, either a equals 0 or a minus 1 equals 0. And this is because integral domains do not have 0 divisors, so one of these two things has to be equal to 0. So we either have that a equals 0 or that a equals 1, which is what we were trying to show, that if a squared equals a had to be either 0 or 1. So the only idempotent elements of an integral domain are 0 and 1. Alrighty, let's play with some fields and let's play with some characteristics. So as we start this, it might be helpful to just remind ourselves of some definitions and some theorems that are useful here. So a field is a ring with unity, and every non-zero element is a unit. Remember that all fields are integral domains. Units are elements that have multiplicative inverses. And then a characteristic, the characteristic is the least positive integer n, such that in x equals 0 for all x in R. And then we had two theorems that were super useful from what I had told you in the notes, and that was theorem 13.3 and theorem 13.4. So theorem 13.3, just a very brief overview of it, is that the order of 1, if 1 is your unity, is equal to your characteristic. If the order of 1 is infinite, then your characteristic equals 0. And 13.4 says that the characteristics for integral domains, and thus for fields, are 0 or prime. Now, when we're talking about the order of 1, we are talking about the additive order of 1 here. So, what are some things we know? What is the order of 1? Is it infinite or is it finite? Well, we have a field that has a finite order of 2 to the n. So if our field has a finite order, then the order of 1 has to be finite. So the order of 1 is not infinite, so the characteristic is not equal to 0. Now, we also know that the order of 1 has to divide the order of our group, of our ring and our field. And we can think of it as a group and be able to think back to Lagrange's theorem, because we're talking about the additive order of 1. So if we think about theorem 7.1, Lagrange's theorem, the order of 1 has to divide the order of our field, which is 2 to the n. Now, we know that we have a field, which is an integral domain, So that means our characteristic is either 0 or it's prime. We know it's not 0 because the order of 1 is finite, and the order of 1 has to divide 2 to the n. What is a prime number that divides 2 to the n? Prime number that divides 2 to the n is 2. Therefore, the characteristic is 2. So really, we were able to just reference 3 theorems that we know. Keep in mind that all fields are integral domains. And we were able to then say, hey, we know the characteristic without knowing really anything about our group besides that its order is 2 to the n. Alrighty, so that is chapter 13 examples. If you have questions for me, make sure that you send me an email, and I'll be looking forward to seeing your homework and seeing any questions that you guys have for me.